Hi, this is Sri Ramulu, DL in Physics. Today's topic is before entering this into this topic, please share this video, like it, and a comment. And before doing these things, don't forget subscribing. So for encouragement, please subscribe it. And now, explanation of atomic spectra. So we learned atomic spectra. But what is, how does atomic spectra forms, and what are things present inside the atomic spectra? Let me explain them. So there are the two things we must know by using this. What is first? Orbit diagram, and the next one is energy level diagram. So these two things may present in explanation of atomic spectra, right? So what are those explanation? First, let me explain brief. All right, now orbit diagram. So see, the side box is given many diagrams, many orbits. See, there are these orbit, like this. There are the many orbits are there, but it is from here to here only half lines are drawn. So it means they are fully drawn, but there is no space this side. So that is why. So these things are drawn up to here only. So don't think it as a half diagram, right? And now let me come according to general expression of radii different orbits, right? Radii of different orbits. See, so already this equation is derived where in a Bohr theory, right? So if you want to watch the video, previous video I kept in the YouTube also. So radii Rn is equals to n square h square epsilon naught pi by m e square, right? So this is, and next a few stationary orbits are drawn. See, these are the stationary orbits. Stationary orbit means the orbit which contain fixed energy, right? Constant energy. So those orbits are called stationary orbits, right? The orbits marked as n1 is equals to 1. See, n1. So here there are the many numbers also given. n1 here, n2, n3, n4, n5, n6, n7. So like these 7 orbits are drawn, right? Suppose n1 is equals to 1 is called ground state. So first to n is equals to 1 is ground state, and it represents the stationary state of unexcited state. It is also stationary state but unexcited. So this state cannot excite. Mean whatever elements or whatever electron present in the ground state are n is equals to 1 in the first state, then if the energy, if they absorb the energy they cannot present there. Where they go? They may jumps from 1 to 2 or 1 to 3 or 1 to 4, 1 to 5, 1 to 6, like this, right? Now next, the orbits corresponding to the n1 is equals to 1, 2, 3, so on are called k element. N is equals to 1 means k, right? 2 means L, 3 means M, so on, like this. These things represents. And next, suppose by some process such as thermal agitations or impact of particles, such as impact of particles, not articles, impact of particles such as photon. It is a photon, right? Electron, proton, etc. So these are the what particles. If they strike to the atom, then what happens? Or thermal agitation means with the thermal energy. Then what happens? See here in the second line, revolving electron in hydrogen atom is removed, right? That is removed from the ground state only. And then what happens? A removed electron can jump to the higher energy state. Say that is let that is higher energy state is n is equals to 4th one, right? So that electron is jumped to the 4th state. Now, and 4th, now see this point. Now the electron, right? Now the revolving electron of atom possesses more energy than the normal state and is less stable, which is n2 is equals to 4 is less stable comparing to n1 is equals to 1. So electron is present here, it is jumped to the here, and in this state electron cannot stay more time, so that is a less stable state, so that means it come back. Okay, how much time it stay in this ground, in this state? See, that is also given, how much time it stay. Electron now returns to the ground state in about, so electron may stay in the n is equals to 4 and 2 is equals to 4 to state 10 to the minus 8 seconds only, and it comes either in one step or in intermediate steps. What are those intermediate step? Let me explain. Example, so it jumps from the n4 to n1, it may come directly fourth state to first state, or it is single step only, or alternatively it may jump to the second state and next second to the first state like this, or it may jump fourth to third, third to 1, or it may jump fourth to third, fourth to third to 2, 2 to 1. So finally where it has to come, it must come to the first state, right? First state means that is a ground state. So where from here to here, so how many path for how many steps it follows? It may follows these steps, so the possibilities, if it comes it follows this path, so then this path cannot be followed, so any one of these path may follow, that is the meaning of this, right? Next, in each step electron radius energy difference of two states in the form of, it is in the form of radiation whose frequency is given by this equation, right? So here the what, in each step electron is where it is from fourth to third, if it jumps from fourth to third, then what happens, it may release energy, or if it jumps from fourth to directly 1, then it also emits energy, but its energy more very much greater than this one, then more energy will be released. Okay, so from fourth to third means less energy will be released, so but frequencies are different, their frequencies are frequent, depends upon frequencies. And the next last one, in this the different members of series are obtained by like this only we obtain different series. He is saying different series means what are those series? See, Lyman series, Balmer's Lyman series, Balmer series, Paschen series, bracket series. So electron from the, let it is a fourth one, from fourth to directly it jump to the first, then it release the energy, or it jumps from here to directly first one, it releases, or it may follow like this also, from this to here also, or here to here, or here to here, there is a possibility. Okay, like this. Then these are the names has come. Why? Because those scientists are observed this pattern. Okay, next, energy level diagram. See the energy level diagram. In the energy level diagram, in this diagram shows that the discrete energy state to the atom are represented by the horizontal lines, and a transition of an atom from the one state to other state giving rise to spectral lines shown by a vertical line joining the state involved. What he is saying, this diagram shows that discrete energy means see, horizontal lines, horizontal means this one, this one, this one, this one, these are the horizontal lines. Okay, and these horizontal lines are having fixed energy, so that is why these are also called as discrete energy, discrete lines, right? Discrete means they have the fixed value. Okay, discrete. And the next, transition from higher energy level to ground level giving rise to the Lyman series. Higher, so either from here or from here or from here or from here to here, if any transition occurs, then the series formed means suppose for example electron may jumps from here to here, electron may jumps from here to here, electron may jumps from here to here, So here when it jumps from here to here, then energy release, then also energy, here also energy release. So many energies they forms a spectrum. So that spectrum contains many cell, many frequencies or many wavelengths, different wavelengths. So that is observed by the Lyman. So that is why that is called Lyman series, right? So that is the thing. In the same manner, other series are also observed. If instead of coming of higher energy level to here, if it ends here only, then they forms Balmer series. Here to here, here to here, here to here, like this. If they ends here only from different energy level to here only, then they form passion bracket fund, like this series are observed. And next, the other series are also indicated in the diagram. So these are these series. Next, this line emission spectrum line, these are all observed by the lines only. So that is why line emission spectrum of hydrogen atom is completely and correctly represented by the Bohr theory. So what I am explaining, it is complete with help of the Bohr theory only, not with other theory. That is this thing. And next topic in this only correction for the finite mass of nucleus. What is the meaning of finite mass? Why correction word is used here? Generally, in atom nucleus present and as well as electrons present, but nucleus present at the center of the circle or orbit, and electron revolve around the orbit continuously. Okay, but when the nucleus has a huge mass, then it cannot revolve. But when it has a less small mass, finite mass, then whatever particle present, whatever nucleus present, they also rotate about a fixed point or an axis. Okay, so when it has less mass, then only they rotate. So how much it contains the mass comparing to the electron, that is given here. In the Bohr theory, it was assumed that nucleus remains fixed at the center of the circular orbit, right? Circular orbit. Okay, this only, see, in Bohr theories it was assumed nucleus remains fixed at the center of the circular orbits, fixed. But this can only be true. So about statement is true when nucleus has infinite mass. When nucleus has infinite mass, then only it stay fixedly. It cannot rotate or it cannot revolve from that point. But actually nucleus is, see how much greater it is comparing to, is 1840 as heavy as the electron on account of finite mass of the nucleus. See, comparing to the electron, how much greater it is? 1840 times. Okay, so that was greater only comparing to. So that's why it is a finite mass. It has a finite mass only. Okay. So both electron and nucleus rotate about the common center of the gravity with the common angular velocity. So there it has finite mass. Nucleus has finite mass. So that is why it starts rotating about axis of rotation. Its axis of rotation. So about this not only this nucleus rotate and also electron rotate. For both axis of rotation is same, and how much with velocity electron rotate is the same velocity here, nucleus also rotates. That velocity is what? Omega, angular velocity. Right, now the axis of rotation is on the line joining the nucleus and electron, right? And next, here the C, Rn and Res are given. Rn and Res. Re means E indicates electron, N indicates nucleus. So Re means the distance of the electron from the axis of rotation. From here to here distance is Re. And from nucleus to this point, that is Rn. Okay. But actually one more distance is there. Distance between nucleus and electron. Nucleus and electron, that is denoted by R. Okay, so see, let in next step. Let capital M and a small m be the masses of the nucleus and electron respectively. So nucleus is somewhat heavier than the mass, so that is why its letter is bigger letter. And next, let Re, Rn be the distance of the electron and nucleus from the axis of rotation. From axis of rotation, these are the distances. right? Next, right? So like this, RE, RN be the distances from the axis of rotation only. Next, a simple theorem on center of gravity. So what is that theorem? M, mass into distance, that is a theorem, right? So here if you observe what is given here, see this is the this is the formula. What is that formula? How does it comes? M is the capital M is the mass of the nucleus, right? Capital M is the mass of the nucleus, small m is the mass of the what? Electron. But it is heavier, it is smaller. So for heavier, what I am doing, I am multiplying with the smaller. For the smaller, I am multiplying with heavier. So it is a more distance, it is a less distance. So that is why these two are equal. Okay. Now write masses one side and distance one side like this. If R be the distance between the nucleus and electron, then R is equals to Rn plus Re. So if you see the diagram, then you can understand easily what R is the distance where to where from nucleus to electron, right? R is the distance. But Rn is the distance from nucleus to axis of rotation, and Re is the distance from axis of rotation to electron. So now see that these two things, see in the diagram, here to here distance is R, but here to here is Rn, here to here is Re. So it is a more distance, it is a small distance. From the equation, say let it is equation 1 and equation 2. From the equation 2, we can write Rn is equal. So what is here? We have to calculate here Rn and Re values we have to calculate. Okay. Now for this what I am doing, from equation 2 only I have written like this. Substitute this Rn value in the equation 1, where here. Okay. Then it is thick. Why we get like this? By solving this, so we get Re value only. We must write it is Re. So if we solve it and get it Re, so finally what we get? We get like this, Re. Now from the equation 2 and 3, again third equation, substitute in the equation 2 in the place of Re, then you get Rn value. So like this, here we got Rn value as in this manner. For Re, Rm, capital M here in a numerator, here small m we got. If now small v be the velocity of the whose electron, capital V is the velocity of whose nucleus, and we know linear velocity is equals to radius into angular velocity relation. So these are the relation. Okay. And now we have to use the kinetic energy, total energy. So here the kinetic energy, only kinetic energy. Why? Because electron continuously rotates and a nucleus also rotates. Then what is their kinetic energies? What are their kinetic energies? So kinetic energies of the electron and a nucleus is given like this: half mv square and half mv square. Here mass, small velocity, capital mass, capital velocity. Right? And now next, half mv square. But v, already v value we just now I have written, v is equals to what? R omega. For electron Re, for nucleus Rn, Vn, Rn. So like this, here those things are substituted here, and in the place of Re and Rn, so already Re, Rn values we got, Re and Rn value, it is Re value, it is Rn values, and substitute these values in this equation. Then what we get? We get this in the place of Re and Rn values we have substituted. Okay. And now take the common points. Common points are here. See here, R, small r, capital M. Where? Here, right here. By m plus small m plus capital M. And here also in denominator capital small m plus capital M. But here the capital M, here small m, right? But outside is capital M. Here outside is small m, inside is capital M. But here square term is there, square term is there. So here it becomes m square. So here from m square take out m, and here also small m square, take out small m square, small m, and 1 m will be there inside, right? See here, see, let me explain first one only. R m by m plus m are their whole square, right? Whole square. But take it outside, only m take. Why? Because whole square means here m square. Out of m by this one, out of m square it is r square, right? M square, take m only outside, 1 m will be there inside. In the same manner here also small m come outside. Already here small m is there and capital M is taken, and here small capital M is there, small m is outside taken. Then what we get? See, small m capital M, right? Here common small m capital M, here also common small m capital M, along with r. R is also whole square is r square come outside. Like this it is formula. And inside is here. Here capital 1 capital M remains, here 1 small m remains. Why? Because whole square is there. Okay, this is. And now upside is capital M, and here upside in numerator capital M, small m, here numerator is capital M. But denominator terms are same. Then what we get? We can add them upside. So upside addition, downside addition. 1 will get cancelled. So again we get this one, right? Okay. Now write these terms inside bracket. Then m by m plus m. Right? m by m plus m. And this m by m plus m, m by m plus m can be written as total. It is a mass. Mass by mass plus mass. Mass multiplication, mass addition. So finally we get mass. So this mass is called reduced mass, and it is denoted by mu. Reduced mass is denoted by always mu only. So in the place of this what written, mu is written. So mu is called reduced, Re here, reduced mass. Okay, like this, reduced mass. So in this manner mass is corrected, finite mass. So correction of mass means this only. So here the mass is corrected. In this manner mass is corrected. So up to here only this equation is valid in the examination. Now but here I have taken extra explanation. So that explanation is, see here, extra explanation is expression 5. So just know what we have obtained. For the kinetic energy of the system differs from that in which the nucleus was considered at rest only in the respect that reduced mass mu replace the mass m of the electron, right? So here reduced mass, so capital M and small m product is replaced by with what? Mu only. Now all the expression of both theory will be valid if we replace m by mu. So wherever we get m value, there if you write mu, he is saying like this. Okay, so then that is the corrected. Next, now the wave number of expression of Bohr reduces to like this. Okay, so here this is okay, and from this what it is written like this. Sorry for the disturbance. All right. So right, it is nu bar is now the frequency nu bar is equals to E square. It is already, this equation is obtained. This equation is obtained already. This equation is obtained. Okay, if you want to see it, check it, Bohr's theory. Okay, Bohr's theory is completely reduces where we get a small m, there the values are reduced in this manner, and finally we get like this. Okay, so it is no matter, big matter. And now see the equation 6 and 7. Where is the equation 6 and 7? It is see equation 6 it is, and equation 7 it is RH. It is H is a small h. H indicates hydrogen, right? It is also a small h. So here not possible to write the very small h. So I have written R capital R into capital H, where R is called Rydberg constant, right? So from equation 6th and 7th, what we get from 6th to 7th, there are the certain conclusions are there. So those conclusions, let me explain. First one, following important interesting conclusion. Ion which have hydrogen like structures, that is the nucleus of charge is Ze, and a single electron must gives rise a spectral series similar to the hydrogen atom. Okay, so consider the case singly ionized helium nucleus charge 2e. It should give a series of spectral lines whose wave numbers are given by this one. Okay, it is first generally this equation 6 and 7 valid for only for what single electron, and from helium also, generally helium contains the two electrons. So out of two electrons, if you remove one electron, it becomes a helium plus only. It is also single electron. It also contains when anionic state, it also contains a single electron. Okay, for this only generally Bohr's theory is valid. In this case, the wave number nu bar is equals to nu bar for helium, He suffix, generally we have to write like this, nu suffix. Okay, nu suffix He for helium is 2 square. For helium is 2 square. Why? Because here Z number is 2, right? 2 square, 2 electron present, 1 by n1 square minus 1 by n2 square. Okay, see here 4 times greater it is, where see 4 times greater it is comparing to frequency of hydrogen. It is frequency of hydrogen, it is wave number, sorry, frequency, wave number of hydrogen, it is wave number of helium. So how much it is greater? 4 times. Wave number of helium is greater than the hydrogen. How much? 4 times. Okay, this shows that the wave numbers are 4 times greater or larger as the wave number of the lines in the corresponding series of hydrogen, and these lines are actually observed in the spectrum of ionized helium only, not helium. Ionized helium is helium plus only. Next, knowledge of Rydberg constant for hydrogen and ionized helium can be used to calculate ratio of mass of proton to mass of the electron. Thus, proton mass to electron mass, right? Proton mass to electron mass. RH by RHE. RH means hydrogen, Rydberg constant of hydrogen, and Rydberg constant of helium. Okay, so it is a ratio like this: 1 plus m by m helium by whole divided by 1 plus m by m hydrogen. So if you substitute their values in this equation, and we get m by mh, how much? Mh means mass of hydrogen by mass of electron is 11, sorry, it is not 11840, it is 1840 only, right? 1840. So that means mass of helium, mass of nucleus is how much greater than 1840 comparing to electron. So this is the thing of this. So ratio of thus the ratio of mass of hydrogen atom to mass of the electron is 1840. See, it is wrong, 1840, which is an excellent agreement with the values determined by the other methods, right? So in other method also determined, but they got the exact value this much, this is only. So thank you friends, don't forget subscribing it.